Oh, definitely come in person. Oh my gosh, no. If you have the option to go to a conference, go in person. That's the whole point of conferences.
Hello, I'm Chris Ryan. Thank you for coming. I'm here to talk about C++ under the hood. This is not a talk about C++ and embedded in automotive systems. So just to get that straight. I realized that after I published the title that there was some confusion on that, so I changed it to internal class mechanisms. Constructors, destructors, polymorphic mechanisms, and we're going to do pointer to functions, pointer to member functions, pointer to data, or pointer to member data, which operate different than C pointer to functions and C raw pointers. But we'll cover a little bit of that also. So there's the cute AI picture I did for it. So under the hood, I've always found it's much easier to understand what's happening and why it doesn't happen right if you know what's going on inside. You shove the bits in one side, they come out the other side. Some people work fine treating everything as a black box and it magically works. But when the bits start coming out in the wrong order, it's nice to know what's happening inside to be able to figure out why it's not working correctly. So we're going to talk about internal class mechanisms, the C++ onion, inheritance, polymorphism mechanisms, member data pointers, member function pointers. I gave this talk last week in Norway and went way over my time slot. So I've moved the next couple items to open content that will be tomorrow during noon. And hopefully you guys will be interested in me enough to keep continuing on that. So I've been everywhere, I've done everything. It's like the old Johnny Cash song that I've been doing C++ since the early 90s. C since the mid 80s, and I've worked in every different form of industry. So I have both a hardware and software background. I think that's one reason why I like knowing the internals so much, because I know what the electrons are doing underneath. The C++ onion, it makes some people cry, but that's not the purpose for it. It's the layers of inheritance and construction. It's constructed from the inside out and destroyed from the outside in. Chances are your inheritance doesn't look like this planetary slice of the core of the planet. Probably looks something more like this, which is an onion that with several different objects in there, and each of the internal objects have their own hierarchy. If your onion starts to look like this, your brain on onions, you're doing it wrong. So, important thing to understand, and this is something you probably all learned a long time ago, inheritance is a, and then aggregation is has a. A person has a name, a person is not a name. An employee is a person. So if you do the is a, has a, that will tell you if you're inheriting correctly or not. So say you have three classes. C inherits from B inherits from A, and then you have your base class of A. And you have constructors, destructors, a virtual function, and a standard function. So your base class has a vtable pointer. The other classes, because they inherit from it, that's at the same zero offset. So if you have a pointer to B, it still knows that the 0 pointer offset, and you get your virtual pointer. So each class has a vtable. This is one vtable in the entire system for each class. It is not expensive. Some people say, oh, we got a vtable for every instance of your class. You have 1 million classes, you got 1 million vtables. You got one. It only just uses a few bytes. And most of the time it's modeled as if it were an array of function pointers. It kind of is, kind of isn't, but that's the easiest way to model it, to look at it. You got your constructors, and the constructors for each instance, as it's building this onion from the inside out, sets up the vtable pointer for that instance of the class, and the outer layer is set for each of theirs. The destructor works the same way. The destructor actually sets up a vtable for its class, because presume that we didn't know that there was a D class that had further derived from this, and it had put in its own vtable. And then we start destructing in C, and we went to call a polymorphic function that was still pointed off at D. Things would break, because you don't want to call an outer class once it's already been destructed, because functions it has may be using data which no longer exists. You want it to still exist. So we go to construct C. That calls the constructor for C. First thing it does, it constructs from the inside out. It constructs the base member. Another little tidbit, base classes are members of your class. And every member in your class is constructed in order, basically top to bottom, front to end. So here we just have B, so we inherit from B. The B calls the constructor for B. And then we go drill down to the base for A. And then we actually start doing things. We initialize there was no base for A, so therefore we don't have to drill down anymore. We initialize our data members in order. A gets initialized. A actually doesn't have a constructor, but we initialize it. Curly brackets on there, default initialization. Use them everywhere. They're not expensive, and it'll save you from a lot of bugs. Then we construct the string object in order of declaration. And at this point, the A object does not exist yet. We're just filling out the members. But the moment we get to the opening curly bracket of the constructor, it does start existing. So we set up the vtable pointer. Here it points to a vtable. Then we start running with the body of the constructor. In this instance, it has a function called bar. Bar is not virtual. If it were virtual, because it is effectively a final, it would be a direct call to it, because it knows in the constructor that no one exists beyond this, so it would have called it directly. But here when we call bar, when we're running the bar function, it doesn't know what's in the constructor, and then it's calling a virtual function foo. It looks up in the vtable, or it looks at the vtable pointer that points to the instance of a vtable, and we look up and we're saying we're calling a foo, and then it points back and it calls and executes the foo function. We've now completed the constructor of A, winding back down to where we could come from. Now we initialize the members of B. So the int gets initialized and the string gets constructed. We set up the vtable pointer for B vtable, and that pointer gets assigned in the base class pointer for the vtable pointer. So now when we call bar, or in the constructor, we call bar, it polymorphically calls foo by looking up the vtable pointer, which now points at B vtable, which then we look at the entry for foo, and foo points at B foo, and so that's where we call B now. The same thing continues. We work our way back out, initialize the members, set up the vtable pointer, and we do our polymorphic. We call B statically into our polymorphic call for foo. So we're done constructing now. So you have a fully constructed object. You can go ahead and use it however you want, pass it off to people. When they have the pointer to C, they can turn around and cast that to a B, and you deal exclusively with the B, or they can cast it to an A and get the A pointer and treat it as a base pointer and store it off wherever and do everything polymorphically you wanted to with A. When it's time to destroy it, okay, so remember there, we started inside out. From the outside, we drilled all the way in real quickly to the A, and we constructed A, then B, then C. When you're destructing it, it goes in the reverse order, outside in. You set up remember there may have been someone further derived from us, so we set up the vtable for the world that we know about. which is the C vtable. Assign that to the vtable pointer. We call bar again, and it's locked. The furthest function that it can call is cfoo. We drill down and destroy our members in reverse order of declaration. Outside, the first shall be last and the last shall be first. It's inside out, outside in. So we call the destructor for string. We don't call the destructor for an int. Int does not have a destructor. It's an intrinsic type. We can just let it live on the stack as garbage. We drill down and call the base member to call its destructor. We go through the same sequence, set up the vtable. We do now we're in the body of the destructor. We call the polymorphic, or we call the bar, which then does its polymorphic thing. It's locked. It cannot call outside of B because we're in B destructor. C no longer exists. We don't want any backdoor way of calling to the outside world that may use corrupted data that no longer exists. We destroy string. There again, we don't need to do anything with the int. We drill down to the A, and this just repeats because these are very symmetrical. Set up the vtable pointer, do the polymorphic call, do the destroy, and we walk our way back out. And now we have a fully destructed object that you should never call again and do anything with. Okay, you guys have been doing this forever. A pointer to regular data. It's nice and simple. We'll just hit it real simple here. You can take the address of an int, an address of, being an int pointer. You can even take the address of a member of a struct. Now I always use struct just because they're easier for slideware. Struct and class exactly the same, except for the default access that you have for it. So you can take the address of this int. That will be that one and only instance of that I in that very one and only instance of foo. I think I wanted to make one more point on bar. You can also pass around pointers. You can take the address of P1, which was a pointer, or pass that through into bar. Bar can do whatever it wants with that as a pointer, and it can return a value. And so now we have P3, which effectively is going to be the same as P1. And then you can dereference them and manipulate them. That's nothing new to you guys. Pointer to functions. When you first started taking a C class, your first program was Hello World. Your second one had an if statement in it, and they showed you branching. Your third one was a for loop from 0 to 9, and you print out 0 to 9. Am I exactly on cue for exactly what you did for when you were doing beginning C? Then the next one was you learned how to do functions. The very next thing after that was that you used a sort function and you gave it a comparison function. And we'll get, so you using pointer to functions and you didn't realize it. This is what a pointer to function declaration looks like. You have the return type, it goes outside, back, sorry. No, okay. Yeah, you go outside in. You got the return type and the parameters. Those have to match. That is your signature. This is a pointer of that type. Whenever you give it a function that has to match the signature. Foo is your variable that will be your pointer to function. So here's a simple example. You just take in the main in the bottom, we took the address of the function foo, which is at the top, passed it into bar, and there's our declaration. Int pfn, pointer to function, with one parameter in this case, and we turn around and we call it invoking it by just putting the parameter or the parentheses on there and passing a value to it. It increments it and sends it back. What is returned from foo? Notice I did the increment after. It returns the value before it's incremented. The incremented value gets lost. Okay, here's another example of almost the same type of thing, except for in main, you can see we actually declared a variable and then passed it through that way, because you can make your own variables for them and do as you want to with it. But to make it a little simpler, rather than having to type that big declaration of what a function variable looks like, you can put it in a type def. Because many times you may have a dozen parameters and a complex return, and some of the parameters could have actually been pointers to functions that you pass in. So do that all via the type def. It's a lot easier. You can just say pfn, so we have a pfn type with a pfn variable, and we take the address of foo and assign it to it. Now, this is all C. C is a little, I won't say sloppy, but not particular. You can put the pointers on the wrong spot. Get rid of the pointer in the type def and declare it down below. And then where would you take the address of foo? You don't have to do the address of foo. It automatically decays to a pointer. C++ does not do that. Okay, here's that sort we were talking about that was your fourth project lab you did. You give it an array, you count what the size is, and what the size of each element is, and you give it a comparison function. It just treats them as void, so you have to cast them to the right one. So you compare your left hand A to the right hand B, and it calls them all, and it does the sort for you and shuffles the order of the array. And then it returns it to you and you spit them out. So the compare in the end of the qsort line is the address of compare internally. That's pointer to function. Your fifth lab, when you were first learning this stuff, you were doing this already. Okay, the pointer to member function. Now, they look very symmetrical of regular pointers and pointer to function, but when you call a C++ object or class or struct, you always have to use an object pointer or object reference, a dot, for your object to deal with. And so these are very specific. They will only work with your type of class and your member in that class. So here's a C pointer, and we're trying to take the address of foo : bar. That does not work because it's a wrong type. What we have to have is we do a type def, and we say foo : star pointer to member function. It's PMF. It's somewhat my own nomenclature. A lot of other people use that also. And so then we create an object, or foo object in the middle of foo. We initialize it with the value 10. And so we call this object on foo dot pointer to member function and give it an argument. It does an addition and returns them. Okay, so that is actually taking the address of the function, and you pass it the address of the object and whatever data you wanted to. What if this is a polymorphic function? What function address does it take? Well, you can't take the address of both of them. You can't take just the base because you would be calling the base directly and wouldn't be calling polymorphically. And we have it's actually a foo2 object that we have that we've instantiated there. When we call that, we're actually calling foo2 dot pointer to member function of foo. And you can do that, mix those because of inheritance. But we should really be using the base pointer if we want to prove this using polymorphic. So we call the pfoo, we make a pfoo and call off of that. And so before we were doing the dot, the reference nomenclature, this is the arrow, so it's a pointer of. So pfoo arrow to the object, and then we're calling the member function of foo, which is in the base. But there again, this is a virtual function. We want it to call the derived. How does it know to do that? Oh, actually, I wanted to back up and show you something else here quickly. The second line, we got the type def, and we declare the pointer to member function. That's so C. We like using. We're better than that. We're C++. Apologies to my C friends. So we can do a using, and it works better. But something else, we have the type def or the using at the global file scope, that's declared from there on to the rest of the file, regardless of what scope you're in. We can put it inside of foo, and you have to use it referencing that you're in the scope of foo. So now if you notice down in the first line of main, it's foo pointer to member function type, then we have our pointer to member, and we take the address of our bar function in foo. And we're calling that off of our pfoo object. So here's how we've already covered is the base class has a virtual pointer, a pointer to our virtual table, and it points to our static array of functions. In this case, we have foo : bar and foo2 : bar. So the way it knows which one it's going to call, it provides us with an extra function. The compiler is great about giving us all kinds of functions, whether or not we think we need them. It's a thunk. A thunk is a redirect function. So when we take the address of bar, it says, oh, that's a polymorphic function. I know you really didn't want bar. I'm going to give you what we have in the comment in the green. I'm giving you the address of bar thunk. That's not what they call it. They have their own little, each compiler has their own different name for it, but that's what we call it, what I call it. What it does an indirection of where it looks up the vtable, it gets the address, the index of 1, and then it calls it passing the parameter through. So we set up the pointer to function. Then when we go to invoke it, it uses variable pointer to member function. It looks up the vtable and figures out which function, the vtable pointer figures out the vtable array, which function we're going to use, and then we invoke it and call it. So it knows to call the derived function here. Now, C has raw pointers, and you saw before where we did the address of foo.I. That was to that one instance of that I in that foo instance. C++, we can do it better than that because we want it based off of objects. And we want a pointer into our object, but we don't necessarily care or know which object it is that we're doing at this point. And which brings up the axiom of fundamental theorem of software engineering. Any problem can be solved by adding a layer of indirection. So we have our pointer to member data. So without using the pointer there, you can do a foo1.a and get at the instance of the a in foo1, or the .a of foo2, or we could do the pointer to the object, pfoo2, or pfoo1 pointing at C, and pfoo2 pointing at C, and get the value back from that. But if we wanted to be clever, you say, well, what if I don't know which member I want to point to get the value back? The first example, I want to get the value of A. And so we can do foo1 dot pointer, member data pointer of A, or foo arrow member pointer of C, and that will spit them out as appropriate. Now, notice this is not the address of an instance, it's the address of A in the struct or the class. It's the capital F, it's not a lowercase f. Now, why would you want to do that? You could handle a struct, each member in there generically. Okay, which actually brings up a question. What is null? Come on, someone tell me what null is. Is it 0? Is it? It's C. Null is defined as 0. But the standard never actually says it's 0. It says it has to evaluate if it's assigned, it evaluates false. If it's not assigned, it evaluates as not false. This is C++. This is what we use. So this does the same thing, but our way. So is it 0 too? No, it's not. Well, most implementations, it does do that. But they've always been afraid when writing the standard of saying, someday we're going to find a platform where null isn't 0 and it doesn't make sense. So we're not going to actually say what it is. We just have to say how it's evaluated. So here in the first line, we got p equals null pointer. And when we go to evaluate that, it says 0. It's not assigned, 0 or true. Now, in P on the next to the last line and the last line is assigned to A and assigned to B, and so it returns true. It has been assigned. But where we actually set these up of the sign P to foo : A or foo : B, and we cast away what the value of the pointer is, we look at what the pointer is, and the pointer is 0, 4, 8, 12, and this is assuming the 32-bit int. Now, if you look at that and look at our struct definition at the top, so we got int A, B, C, D, E, no E, sorry, got carried away, that you very quickly realize those are offsets into that struct. It's not really a pointer. We will have our data member pointer, our pointer to our object, and then an offset from it. So this is our extra layer of indirection we're doing. But we already just said in the first line, when it wasn't assigned, it returned 0. But we just looked at it here, and A has an offset at 0. So which one's null? Shouldn't the first line of the bottom 4 be null? No, because if we actually take a null pointer and cast away the value of it, it stores a -1. -1 in memory is how null is represented. So now you can tell your friends null is not always 0. In this case, it's -1. Because if it was 0, you wouldn't know what it was. Whether it was just an index to the 0 offset, or whether it was actually not assigned yet. Okay, so this is the side we just already saw where we assign the pointer, foo : pointer to A, and then the same one to B. And so we can look them up indirectly. Okay, why would you want to do that? Remember our friend, the sort routine? This is the C implementation. What about the C++ version of that? We have some mechanism which goes out and gets us a collection data, and we pass our collection to sort. And sort says, we give it a lambda, and we want to compare the left-hand side A to the right-hand side A. Now, if we also wanted to sort on B and sort on C and sort on D, we would have to give it 4 functions. Or we could pass in the lambda that we wanted. And so we do sort our data, and what each of the lambdas was, it would left-hand side A, right-hand side A, and B, C, D. Same way. Well, what if we do that programmatically and pass in the data member pointer to the sort, and we say sort on A, it calls it up here, it passes it into the lambda, so the lambda can get it, we pass it in through the capture, and we can do left-hand side dot the data member pointer, or right-hand side data member pointer. Okay, now it's cool that we can sort by any one of those we wanted. What if we wanted to sort by B and then C? This is a sort which can take multiple parameters. We wanted to sort by B, then C. So that calls into the sort. We capture this, the list of all the different types, and then we capture that in the lambda and pass that into the compare function. In the compare function, we strip off what the first comparison is, which I called T : key, and then auto the rest of what all the other types were. I compare left-hand side to the key to the right-hand side of the key. So greater than, less than. Obviously here it's still equal, so we need to go get the next index or key that we're using. So we drill down. We've already done the key, so we'll go for the rest of the arguments of the keys package. That turns around and calls back. We strip off the first one, and this does the templatized recursion in generating the code. So we have a comparison that can compare by B and C. The same mechanism works if we wanted to compare by C, D, and E and do the sort, and it can do a multi-column sort. Okay, I actually came in under time. And so this was where I was going to cut off. and I was going to cover the rest of it later in the open content session, but sorry, I'm overshooting. Let's talk about the memory object footprint and what the vtable mechanism is. And that's a table full of mechanisms. So, now if we just had our structs for A and B and C, and they each had an int, the memory footprint would look something like capital A with member A, and it's at the 0 there is the offset. If B inherited from A and C inherited from B, they're nested inside of each other, outside in, inside out. But to make this a little more interesting, we want vtables in each of our classes. So here's the case where they're not inheriting from each other, and the vtable pointer in the object is at the 0 offset. So if you have a pointer or something, you know you can always find it what the vtable is, even if it's a further derived object and you don't know what that object is. The vtable pointer is at offset A, or pardon me, offset 0. So we had our vtable here of : bar, : bar, or B : bar, C : bar. But if we're going to have a virtual, if you're going to do it right, you have to put the destructor in there. That's just kind of the rules for making a well-formed program that has virtuals. And it's nice if your virtual always goes in at your in the first index. Just stylized why that should go that way. There's no actual firm rule. It could be the fifth thing, but it's nice to put it first. Now, if you do inheritance off of those, you can see B, the green one that inherits from A, still has the vtable at the 0 offset within that. And C, the blue, inherits from B, and C has actually absolutely no knowledge of A, but A has a vtable pointer at the first index, 0 offset. So it's at the same spot. Looks a little bit different when you have members. This is non-inheritance, where you have your basic A vtable, and then your B, you have a member that is of type A, and it carries its own vtable pointer with it. B and A have no relationship other than there's an A in B. So if someone takes an address of your member A, they would be calling virtual functions in the member A. So the constructor, when it sets up and initializes the vtables, there's actually two different vtables here. One is the one for B, and this is the same one for A that is right up here when A was constructed. Make this more complicated. C has a B, and B has an A in it. Each one has its own vtable, and these are the vtables that were set up when each of those was constructed. They don't overwrite each other because they're not at the 0 index from each other. Okay, now here's an example of where we have an A and a B, no relationship between each other, but C inherits from A but has a B member. So it has a memory footprint that looks this way. C can leverage off of the vtable pointer in A because they are the same object. One just inherits from the other. B is a member. You can treat that as its own object, and it has a vtable. But what about this? C inherits from A and B. Wait a minute. Those have the same memory footprint. The compiler knows the relationship between the two of them, that when it sets up the vtable, that the vtable in B is leveraged upon it, and C also has access to it. So C also has access to the vtable at the 0 index, at the 0 offset, but it also has it at the 8th index. And if you notice the vtables, when I was here, this vtable is the B vtable. Here, since C is doing it, this is a C vtable, but for B. So this is A vtable, B vtable that gets stuffed in the A class or the B class. And they both have access to the virtual destructor, and they both can call C:::, bar. But this one has an adjust by the value of 8, and this has an adjust by the value of 8. When you call a function, one of these functions over here, actually, I guess you can't really see it very well, but if you had a B pointer and you call a function in the B object in this, it's going to give you back this pointer at the B object. If you have a function in A and a pointer to either C or A, and you call the function in A, it will give you this pointer for the A. They're going to be different values because there are different spots in the memory. But when B wants to call something virtual that's going to throw out to the C, or potentially even that C inherited from A, it needs to adjust what the this pointer will be, and it will do an 8-byte offset. There again with the 32-bit ints we're using here. So here's an example of that. This code is almost exactly what we were looking at there. When we go to construct it, we construct A inside out, and it has its this pointer. It goes to construct B. Actually, let me back up a little more explanation. That diagram we did of drilling down through everything, we really go to construct C first, but the first thing C does is construct its base members in order. And so it calls A constructor, then it calls B constructor. The this pointer, this is the same object, but the B this is different than the A this. And when we finally get out to constructing the C and A coexist so they have the same this pointer. Therefore, this object actually has two this pointers. When we're actually running here, if we have an A pointer, when we cast it to an A pointer, the C pointer to that, it has the same address as the A and the C did here. And we go to call bar. This is what bar would print out. Bar happens to be a polymorphic function, so it throws to the C bar, and that C has the same address as that, but the C bar turns around and calls foo. Since C inherits from B, it has full access to call all the functions, the public functions or protected functions in B, which is foo, but there again, it has a different this pointer offset. It knows it's calling from the outer class to the inner class, and the call will actually do a +8 on the address rather than subtracting back off. Now when we go to call the C foo, we get exactly what we expected because we're calling off a C, and then it calls the B foo again. The C calls B foo, and we get the zero off the D0 number rather than the C8. Destructing, we call the virtual destructor off of B, which ends in the D0, but we want to destruct the whole object, which is at C8. So the virtual mechanism fires, calls the derived destructor in C, which it destructs the outer object, then it calls the destructors in reverse order of the member declaration, the basis. So it destroys B, then it destroys A, and there again it does the magic fix up on the this pointer. We got 18 minutes, we can handle this. We may not actually need to do the session tomorrow. This is a bonus subject for internal mechanisms. This is stack frames, not broken window frames like that. But when you have your stack, when your program goes to start up, you have a startup routine that pretty much normally you don't know what it does, but you know it's going to call your main. And so main passes parameters, your argv, argc. It pushes the argv first. It goes this is a theoretical calling convention and pushing stuff on the stack. Some calling conventions will pass parameters in registers and return everything via registers. This is more of stack based, so because you can see it better on stack. So not everything this is somewhat what an old style x86 would have done. So we push the argc, then we actually call main. It pushes the return address and saves that. And the first thing we do in the function main is push what the current base pointer was. And we'll use the base pointer as the frame of reference that we will reference all of our variables in A. So we have our parameters that we've saved in A, or that are on the stack that we got called with. And so, we also, since we wanted to use our reference for where we're at. Our stack pointer has been pushed down far enough that we want to save this into the base pointer exactly where we're at. The stack pointer keeps building down. So we know that we're going to have, and I kind of have some dots where we didn't really know, but it's local variable 1 through local variable n. They take up that many. Assume it's 3, so we add the size of the local variables and push the stack pointer down even further. So we have space for 3 32-bit ints, just made up numbers. So we got our the code over here that you see running. Now we go to call a function. So we pass the parameters, again, right to left, push, call, and we call the new function, save the return address. We save the base pointer. We set up the new base pointer for this function based off where the stack pointer is at. We add the size for the local variables again, and we push the parameters. We call the next function. We save the base pointer address for that, and we finally get to the point where our function is going to be getting close to being done. So we would return the return mechanism. Is typically to put something in the AX register. When you return, whoever you called you would grab that value out of AX and store it probably in a local variable. My super short example here, I don't bother to do that. I just return the value again and again and again. Our instruction pointer is pointing in the middle of func2. And you can take that and look it up in the map file or the symbol table and look up the name saying we know we're in func2. However, we also know what our base pointer is. And from our base pointer, that points right there, the address up from that is the return address of who called us. So we can take and look up that address, and that says that's a func1. So we walk up, the base pointers link together like a linked list, back up the stack. We take our base pointer, one up from that was the return address of who had called us. And that says that we're in main. And we look up again, and we know we can look up the return address, and we say that came from the startup routine that called us. And it eventually links all the way back up, and at some point you hit a 0 in their stack for their base pointer, and it stops. So this is walking the stack frame back up and how this walking the stack works, and how you can know all the functions you came from. Since we have our base pointer, any parameter that was passed into each of the functions is at a base pointer minus an index. Any local variables is at the base pointer plus an index. Remember, stack grows down. So that's how you can, with each base pointer, you're walking the stack, and this is what your debugger does. It knows what these variables are. When you're looking at the stack, it's only at an offset. You would have to have the symbols to know what the exact data was at that point and how to interpret it. So we load the AX register, we take the base pointer, because remember the actual stack pointer was further off down here. We just don't care about the local variables anymore. We've already computed our return data. So we pop with the base pointer, push that into the stack pointer, and then, so the stack pointer pushed to where it was, the items that read fall off the bottom of the stack. There's bit turds that are left on the stack, and your garbage that the next guy's going to spy on you and get your data. That's where they were from. So we get the base pointer back. So we loaded the base pointer. We pop off the stack the return address. We return to where the next instruction after we got called from. And we progress walking our way back up the stack through each of the functions. Remember, the AX register had what the return value is. in real life, we probably would have actually captured that, stored it in a local variable, and done something with the return value. I didn't bother to show that here because that's not the important step of seeing how each of the stack frames are built up and destroyed. And this just repeats of restoring the stack pointer, restoring the base pointer back to where you were coming from, and walking back your way back up the stack again and again and again until you get back to your function that had returned the AX to it. And it actually calls an exit routine, passing the value that was given back to it in the AX, and that's what you see as your error level at your command prompt when you wanted to see that. Okay, so since I'd added that back section in, we got about 10 minutes left here. I'm open for taking some questions. People have questions about what I was talking about, or did I describe it so well that I didn't need to, or did I just totally confuse you? Yes, the microphone, please.
Hello? Oh, great talk. I just had a question. If there's no virtual, or any inheritance things, does the compiler still have a vtable for each object? Or?
No.
Okay.
It only gets a vtable if there's a virtual function.
But even if it doesn't inherit anything, or do anything,
correct.
If
Yeah, because you're
virtual, it's got a vtable.
Correct. Okay. That's where your base pointer has its vtable, or your base class. Your base class doesn't know there's going to be anybody ever derived from it. I had the A,
right,
B,
yeah,
C. There could have been a D somewhere off of that, but we don't know about that. Someone could have inherited from that and did their own thing. So yeah. Another little tidbit, just so you know, the RTTI, the runtime type information, is stored in the vtable. They're linked together. If you have a class that does not have any polymorphic functions, and therefore there's no vtable, there's no runtime type information for that object. And that's because there's no inheritance, therefore there's no casting it up and down the chain, so it doesn't need to look it up to make sure that it's safe. Because, yeah. More?
That's it. Thank you.
Thank you. Yep. Yeah, if you want to, you can start building. Oh, actually, we got someone over here, so yes.
Hi. Thanks. Very interesting talk. Learned a few things I wasn't familiar with. But just going back to your slides with the showing stack frame and base pointers, didn't quite make sense to me the signs on your offsets from the base pointer.
Yeah. Stack grows down.
Yeah.
So that's a higher address at the top. So say that it started at address 1000 as we're growing down.
That's right.
It's subtracting off, in theory, 4 each time. So it's 996, 992. So the base pointer.
So from the base pointer, your parameter offsets would be positive, wouldn't they? Because we're looking to higher addresses.
You're right. I think I did hose that. So. And some of it gets confusing because the stack starts at a high, typically, nothing says it has to, but typically starts at a high address and works its way down. So, yep, bonus point. So, okay.
In your example with the A and B and C that inherit from each other with all the colored boxes, that was very clear, by the way, thank you. If C inherits from A, and therefore its vtable pointer is at address 0, if C itself defines additional virtual functions that are not in A, does that go into the same sort of like the A vtable? If you could.
No, well, okay. If in this example here these are all inherited chain all the way up. If C added additional functions, it would just tack them onto the end of its vtable. And A and B would not know about these additional virtuals, so therefore it wouldn't matter. You couldn't call with using an base pointer, call Zaz function because A doesn't have a Zaz. So it would have to be the C pointer that would point at that would have a Zaz function. So yeah, so it would have additional arguments there.
Got it. Thank you.
Okay.
Thank you so much for the talk. I found these vtable diagrams most helpful. 2 quick questions. Number 1, does the C++ compiler see the vtable as a type, or is that some sort of special other thing?
It's implementation specific. The standard never says vtable, never says vtable pointer. That's just the obvious implementation that everybody's gone with. If you really wanted to, there's mechanisms where you could do data structures of climb through and do comparisons of names and do a dispatch off of that. This is just the vtable is the obvious mechanism, and so that's what all the compilers happen to have used. So they are actually a strict type, and if you my frame of reference is Windows, and the Visual Studio, when you stop and you step in assembly, you can see the vtable in an object, and you can see it assigned that it's pointed to the vtable of that class of object. Mm-hmm. And so since it's in a named type, it is strictly, will only bind directly to that address. The arguments in it, I was saying that the vtable is many times modeled as an array of function pointers. You could look at it that way, but also each of those entries in there is of a very specific function pointer type. And so you can't call the one index or the zero index, say the zero index is a destructor, but you wanted to, but you happen to call it with some just address of, you went in and you hacked it and you stole that address out and you called it with an extra parameter. The function you were calling wouldn't know how to handle it and it would puke all over the place.
Right.
So therefore, those are effectively strictly typed, but it's mostly because the compiler knows how to handle them. And that index 1 is always for my foo function, and index 2 would always be for my quaz function. So since they're actually not specified, the compiler is free to do it as it wants, and it knows which index those have been declared in, because they're again in order that they were declared in the class.
Okay, so since you're using indexing into a function, really that's an associative.
It's an associative. We conceptually look at it as an array. Uh-huh. Device drivers back from the good old days, a long time back, the very first function thing they do is they return a pointer to a function table, which is just an array of function pointers. Each one has a different function. They all happen to have very similar signatures, but whatever index 5 handles function 5 of the of that particular device driver, it knows what the signature is, and it turns around and casts the pointer to the right type with the right number of parameters. Okay. So that's a manual mechanism of doing the same thing. The compiler knows that, and the compilers probably internally keep it as a strict type, but it's not, because we never actually really see that type. That's all hidden mechanism.
Okay, one last question.
Yeah.
Does adding the keyword final to C here affect the layout of C in any way whatsoever?
No, it does not. What it does is it knows that any call, say, derived in D, there's not going to be any virtual function beyond it, so it can directly, statically link to the highest derived level of foo and directly call it, short-circuiting having to go through the vtable.
Okay, thank you.
Yeah.
In the case of multiple inheritance, say I want to call a virtual function, does that have to go through all the vtables? Or compilers can maybe optimize such that it can have an association lookup?
This one, if you're pointing at a B object, and it will look up the function index, the vtable index, the 0 for the virtual destructor, or the first one for bar. If you're pointing at an A, it would look up and look in the A vtable, the C::A vtable, which would point directly to the vtable for the virtual destructor of C and bar. And also just another little thing, we called that a virtual destructor, but it's only virtual because we treat it as if it's virtual. These functions over here that are declared in this are just plain normal functions. The only thing that makes them virtual is that they're in the vtable and it knows where to look. If you're pointing at A, the vtable, right here, it would look up in the C vtable because that's where it's pointing at and know that it needs to call the virtual destructor, the function C, by looking that up. So, but I confuse that enough, or?
That makes sense. Thanks.
Yeah.
Thank you. Love the talk. So I think it was the first vtable slide you had up where we had multiple inheritance and there were 3 vtable pointers for C. And then in the second slide you showed...
Okay, and actually I do want to point something out, and I know this is going to come up. When you do multiple inheritance, if A and B had both inherited from the same further base object, that gets a diamond configuration, which makes this really messy and nasty. To get around that, you can do virtual inheritance, which gets rid of one of the bases. And that's even more complicated. I avoided that situation entirely by not addressing it. Is this where you were going?
That was one of my questions.
Okay.
So the other question was, I think if you go back 2 slides to one of the first diagrams you had up. Yeah, so here,
okay.
One more back. Yeah, perfect. So here we had in C 3 vtables.
Mm-hmm.
What changed between this and your next example where we only had 2 vtables inside?
Well, this is,
or the next slide.
This is B contains A.
Oh.
So A has a vtable and B has its own vtable. And this is assigned to the A vtable, the same one that was here. Here we have the C object, which a C contains a B and a B contains an A.
Okay.
And so there is no inheritance and no relationship other than it contains within each of these pointers,
I see.
or these classes.
Awesome.
So,
thank you.
yep. Okay, I believe we were out of time. I will take questions at the floor here for a few minutes, but then there's another talk coming in here in half an hour. So, thank you. Oh.